This video is all about the normal distribution, so please don't try to put a rat down my shirt. Today we're going to learn about how to simulate correlated normal draws, and you are going to invent the Cholesky decomposition all by yourself. The point of this is twofold. One is to learn something that's practically useful. Correlated normal draws come in very handy in lots of different simulations. But two is to build up some intuition for the multivariate normal distribution. It's a really important building block in probability and statistics, and in my experience, students can find it a little bit difficult to understand. Let's start off with a review of notation. A mean vector is a vector that stacks the means of each constituent random variable in a random vector x. So a random vector x is just a vector of random variables. I'll call them x1 through xp. And the mean vector, which we write expected value of bold x, is just the vector that collects the expected value of each of those separate random variables. The variance-covariance matrix of a random vector x is the matrix whose ij element is equal to the covariance between xi and xj. Because covariance is itself symmetric, the covariance of x and y is the same as the covariance of y and x, this matrix is likewise symmetric. Its ith diagonal element is the variance of xi, and that's because the covariance of anything with itself is just the variance of that thing. The correlation matrix is closely related to the covariance matrix. This is the matrix whose ijth element, not elephant, element, is equal to the correlation between xi and xj. This is likewise a symmetric matrix because correlation also doesn't care about the order in which x and y appear. But its ith diagonal element is 1, and that's because the correlation of anything with itself is 1. All right, now with that quick review of notation out of the way, we are ready to start generating correlated normals. We are going to start with independent standard normals. I'll call them Z1 and Z2. So the mean vector for these two folks here, these two random variables, is just 0, 0. The variance covariance matrix is just the identity. That's because Z1 and Z2 have 0 covariance. And because they have 0 covariance, they also have 0 correlation. The only difference here between well, I guess I should say there is no difference here between the variance and correlation matrices. And that's because these two random variables are both variance 1. So the covariance matrix and the correlation matrix in this case are both the identity. Let's try to simulate this in R. I'm going to start off by simulating a large number of standard normal draws. Then I'm going to pack them into a matrix. I'm going to call the columns of this matrix Z1 and Z2. Each row of the matrix I'm about to create represents a single draw of the random vector Z1, comma Z2. So I usually write vectors as column vectors, but now we have turned them on their side, and the reason is that this is typically going to be how R likes to work with randomly generated vectors. So we're going to follow the same convention that some R packages you'll see later use. So here we go. I'm going to set the seed. I'm going to choose a large number n, and then I'm going to make some independent standard normal draws using the R norm command. I will C-bind them together. That constructs a matrix by binding these columns. Then I'm just going to get rid of the original vectors Z1 and Z2 because I don't need them. My matrix is called Z, and I can display the first 6 rows using the command head. If we would like to compute the sample mean of each of these random variables, we can do that. But it would be nice to do them at once for both Z1 and Z2. So we can do that using the function colmeans. That computes the mean of each column of a matrix in R. If we apply this to our matrix Z, we see we're getting something that's pretty close to zero. It's not exactly zero because these are pseudo-random draws. They are not actually a normal population. The variance matrix, the variance covariance matrix, we can be calculated one of two ways. These commands do exactly the same thing. We can either type var of z. When applied to a matrix, that's going to compute the variance covariance matrix. Or we could type cov z. And when applied to a matrix, that is also going to calculate the covariance matrix. Here we see that it is approximately the identity matrix, not exactly. There is some slight sampling variability here. We can also compute the correlation matrix with core of z. And again, it's very, very similar. It should be because, well, we know that this particular example is one in which the correlation matrix and the covariance matrices should be the same. All right, now we're ready to try to visualize the marginal distributions. So these are going to be the distributions of z1 and z2 separately. I will use ggplot to make some lovely little histograms here. And I'm also going to use a package called Patchwork that's very nice for placing plots side by side in an easy way. So here I'm going to make a histogram for Z1 and a histogram for Z2. I think all the commands that you see here should be pretty familiar with perhaps two little exceptions. One is that Z is in fact a matrix, so I need to convert it to a tibble for use with ggplot. So I'm doing that using the command as underscore tibble in lines 4 and 8. The other thing that you may not have seen before is alpha. So that appears in lines 6 and 10. Alpha sets the alpha channel, which is basically the transparency of the geom histogram. So what we can do here is we can allow some partial transparency. That's going to be quite useful later on, so I wanted to introduce it now. Finally, once I've loaded this package Patchwork, I can use the plus operator to put two plots side by side, which is what I'm doing here, resulting in the following output. Looks nice, and you can see the transparency. I can actually view those vertical and horizontal guidelines behind each of the histograms. Now, another way to visualize these distributions would be to use what is called kernel density estimation. If you're not familiar with that, you can click the link on the slide and learn a little bit more. But basically, this is a sort of a smoothing out of a histogram. So whereas a histogram is counting up the number of observations that fall into equally spaced bins of the same width, what a kernel density plot is doing is it is sort of smoothing that out. The bins are discrete, so it's smoothing that out into a continuous function that has the same sort of shape. And the details aren't too important for today, but if you want to make a kernel density plot using ggplot, that's quite easy. You can just replace the geom hist with geom density. So the only thing that's changed on this slide relative to the one 2 slides ago is in lines 6 and 10. I've just replaced geom density for what used to be geom hist. And as we'll see, that makes a lovely little plot that looks quite bell-shaped. It's a little bit wonky because, again, this is a sample of data. If we took an even larger sample, it would start to smooth out even more and look almost perfectly bell-shaped, but this is pretty close. All right. Now, today is not about marginal distributions. Today is about the multivariate normal distribution, so it's all about joint distributions. Now, it's much harder to visualize joint distributions than it is to visualize marginal distributions, and the reason is that they are in higher dimensions. So the previous slide was able to show a kernel density plot, which is a one-dimensional representation. So we can make a graph in 2 dimensions to represent the distribution of a one-dimensional random object. But when we get into vectors, random vectors, things are going to be harder. So there are a number of different ways to try to view a joint distribution of 2 random variables. What I'm going to use here is a 2-dimensional kernel density estimator viewed from above. So this is called the geom density 2D filled. So we're going to kind of take a helicopter tour. We're going to zoom out and we're going to look down on top of the density. So this density is, if we could look at it, it would be a 3-dimensional object. So there would be a height for each combination of coordinates z1 and z2. But the way that we'll look at it, it will actually be in two dimensions. So we somehow need to represent the height of the density. And the way that we're going to do that is using color. So the brighter colors will indicate regions of higher density, so places where the peak is higher. And the only other thing to be aware of on this particular example is line 4, where I'm using coord fixed. This is a command that is going to force the aspect ratio to be 1 to 1, which is useful for distinguishing this picture from some ones that are going to come later in the lecture. So here it is. You can see the joint distribution. It's a little bit wonky, but we have these sort of approximately circular contours. And that's what we should be seeing from a joint normal distribution where each of the two random variables is independent. So here there's no relationship between z1 and z2. It is not the case that when one is high, the other tends to be high, or vice versa, nor is it the case that when one is high, the other tends to be low. There is no relationship between them in that sense. And we can see that the peak of this distribution, which is represented by the brighter colors, occurs around 0, 0, which also makes sense because we know that that is the mode of each of the marginal distributions. So if we were to kind of project this 2D density plot onto each of the axes, well, the peak of the probability would be at 0. That's exactly what it means to take a marginal distribution. All right, so we have now made a 2D density plot. How could we change the means of these random variables? Well, that's very easy. We can just shift them by adding a constant. So what I'm going to do here in line 2 is I'm just going to add 1 to z1, and I'm going to subtract 1 from z2. I do that by indexing into the columns of the matrix Z using the standard bracket notation, where, as you recall, the comma is used to separate the row indices from the column indices. And because there's nothing before the comma, that means that I'm selecting all of the rows. But in line 2, I first select column 1, and I add 1 to it. Then I select column 2, and I subtract 1. So now I'm going to make two plots on the same slide, again using this lovely plus command from Patchwork. I'm going to show the marginals. Now I'm going to show them on a single plot, however. So I'm actually going to use the transparency to show them on one plot, and because we can see through them, they won't block each other, as you'll see in a moment. I'm going to put that next to the joint density plot, so the 2D density plot that we view from above. And as you can see, we have successfully shifted the means. So this orange distribution is now shifted to have its center at -1. And the gray one is shifted to have its center at +1. The contours that we saw before, those sort of roughly circular but slightly wonky contours, have likewise shifted. So now the peak of the density is at the point 1 on the horizontal axis and -1 on the vertical axis. All right, now it's time for you to play around with a little example. This will ask you to look at the child test score dataset that you've looked at before, and also ask you some interesting questions about an R function that does exist and one that does not exist. So as usual, the solutions to all of these exercises are available on the course website, and I would strongly recommend that you pause at this point to work through the exercises and then check your solutions before continuing the video. We've changed the means. Now we're ready to change the variances. Adding a constant does not in any way affect variances or covariances because shifting things around doesn't change the nature of their linear dependence and doesn't change their spread. If you remember the way that covariance and variance are defined, the first thing you do when constructing them is subtract the mean from each random variable. So clearly, shifting the means won't affect those quantities. So what this tells us is that we can just work with zero mean normals until the very last minute and then shift to obtain the desired means. Anything we want to do with variances and covariances is going to be completely unaffected by that shifting. So for that reason, in the rest of this lecture, we're just going to work with zero mean normals, safe in the knowledge that if we want to relocate the center of our distribution, we can just do that at the end. So the rest of the time that we spend here is going to be focused on dealing with the variances and covariances. So let's start with variances. How can we change the variances of z1 and z2? Remember that those started off as standard normals, so they had a variance of 1. How can we change these variances without creating any covariance between them? Well, we just multiply each by a constant. So here I've decided to multiply z1 by 2, and I have decided to multiply z2 by 5. What will that do? Well, that will create a variance covariance matrix in which x1 and x2, which are what I've decided to call these transformed random variables, are still uncorrelated. So they still have a covariance that's approximately 0, remembering that this is a simulation, so it's not going to be exactly 0. But now the variance of x1 is 4, and the variance of x2 is 25, compared to the variances of z1 and z2, which were both 1. When we make this change, we can return to our plot from before using exactly the same code as we previously wrote, but now what we will see is that the contours that used to be circular will become elliptical. So now these two random variables are both centered at the origin. And again, one of them has this orange semi-transparent color. The other one has a gray semi-transparent color. We can see that one of them is more spread out compared to the other. And that is reflected in the plot at right, where again, I am fixing the axes. So 1 unit on the horizontal axis is equivalent to 1 unit on the vertical axis. At least I believe I am. Yes, I am. Coord fixed. Good to double check though. And now we see that what used to be circles, well, has been replaced by ellipses. And that, by the way, is why I wanted to fix the scale of the plot, so that we could be completely sure that when we see ellipses here, it's not just a trick of the scaling, it's actually a change in the shape of the objects. All right, so we know how to shift the means around, we know how to change the variances, but you probably knew that already. The real topic of today's lecture is covariance. So how can we create dependence? How can we create correlation between two normal random variables? Well, the answer is we can combine to create correlation. So what I'm going to do is I'm going to construct two new random variables, x1 and x2, as linear combinations of z1 and z2. So in particular, I'm going to construct x1 as 2 times z1 plus z2, and I'm going to construct x2 as z1 plus 4 times z2. There's no particular reason for choosing those numbers. They're just examples. But the moment that we've done this, and again, we're using our familiar bracket notation to select columns, and we're using cbind to construct a matrix. The moment that we've done this, we can use our covariance function to compute the variance covariance matrix. And what do we see? Well, we now have two random variables that are in fact correlated with one another. Their covariance is around 6, it appears. And if we compute the correlation matrix, we see that the correlation between them is about 0.65. We can now go back to the plot that we've made twice already, and what we're going to find is that we will still have ellipses. The reason that the contours will be elliptical is that the variances of each of x1 and x2 are no longer the same. But these ellipses will be tilted rather than aligned with the axes. This is because x1 and x2 are now dependent. And that's precisely what we can see in the plot. So when x1 is above its mean, x2 tends to be above its mean as well, which gives us this sort of upward slanting elliptical set of contours on the right-hand side of this slide. Now, I implemented this transformation on the last slide by using cbind and by, if you like, manually pulling out columns from my matrix Z of standard normals and multiplying them by constants. But if you think about the operation that I've carried out, that operation is exactly identical to matrix multiplication. So at this stage, if you're thinking to yourself, oh no, I didn't watch that initial lecture on matrix operations in R as carefully as I should have, go back and take a peek at that lecture. It was one of the parts of our first lecture on base R, just to familiarize yourself with some of the basic matrix algebra notation, because today we will be building on that. All right, so what I'm going to do now sounds a bit strange. I'm going to define what I will call X alt. So I'll explain why in a moment. So X alt is going to be T of A matrix multiply TZ. So what is going on here? Well, T is the transpose, right? So that's going to take a matrix and turn it on its side. So what I am doing here is, remember how I told you that my mathematical notation for a random vector likes to treat that vector as a column, but that it is conventional in R to store random vectors on their side as rows, because that means that each column of the matrix is like a distinct variable. And if you think about it, that's the way that we work with data frames and tables. That's the way that we think about a spreadsheet. So that's the convention, to turn them on their side. What I'm doing here is I'm turning them back up. I am sort of tilting them back up so that they're now upright. And so now each of these TZ is a matrix that is 2 by n, and each column is a column vector of a realization for Z1 and Z2. And I have a matrix A that I have constructed. That matrix has the elements 2, 1 in the first row and 1, 4 in the second row that will implement the transformation. So if I take a random vector Z and I pre-multiply it by the matrix A, I will achieve the covariance matrix that we saw on the previous slide. So A times T of Z is exactly what I want to do. Then when I'm all done, I transpose again because, as I mentioned before, I like to store the random vectors in R in the same way that we store data frames. So again, we want each row to be a realization of the random vector. It's a little bit irritating, but you'll get used to it. And this is just an opportunity to think carefully about matrix multiplication, to think carefully about which things are conformable with one another, and then to get some practice with the function t for transposing. So I have x alt, and I claim that x alt, which is an alternative to x, remember I constructed x in lines 1 and 2, I claim that it's going to be identical to x. Well, if you want to check that two things in R are really and truly completely identical, R is actually going to check that the names of the things are identical too. So there are column names in my matrix X. So if I don't want the function identical to throw up a complaint about the column names not matching, I'd better give X alt the same column names, which is what I'm doing in line 10. Finally, I can check, and indeed X alt gives exactly the same thing as X, as it must, because this is just how matrix multiplication works. And now I am ready to define the multivariate normal random variable. There are many different ways that you can do this, but I have a particular pedagogical preference for defining it in the way that I've done on this slide. So my preference is to begin with a vector of P independent and identically distributed normal random variables. I'm going to call that vector Z. So Z is a random P vector of independent standard normals. So that's going to be my primitive concept. I start from there. Now I'm going to define A to be a P by P matrix of constants, and I'm going to define C to be a P vector of constants. My definition of the multivariate normal random variable is whatever you get if you take Z, pre-multiply it by the matrix A, and add C. So that is what I am choosing as my definition. This is not the way that everyone defines the multivariate normal random variable, but it's going to lead to all of the familiar properties, and I think it's a very productive way to go. Some people prefer to define it in terms of the characteristic function. Some people prefer to define it in terms of the density. I like this because what it allows you to do is it allows you to work out all the different properties that this distribution has directly from your knowledge of the one-dimensional standard normal random variable. So you're going to be deducing all the properties of X from first principles, but to keep life simple, we will actually work today in this lecture with the P equals 2 case. Then we can make some nice pictures. It's simple to do calculations, but everything that you do is going to carry over into higher dimensions with the appropriate modifications. So now it is time for the first really substantive exercise of today. So this lecture is really about discovery. It's about trying to discover some mathematics for yourself. It's about trying to take some things that you already know and use them to figure out some other things that you either didn't know or might be things you've seen, but you find it easy to forget. So again, suppose that z1 and z2 are independent standard normals, and we're going to define az. We're going to, I should say x to be a times z, where x is this random vector of x1 and x2. I'm going to define the matrix A to contain the scalars A, B, C, D. And I would like you to now compute the variance of x1, the variance of x2, and the covariance of x1 with x2 in terms of these constants A, B, C, D. Using those calculations, you're going to be able to show that the variance-covariance matrix of x is equal to A transpose. Using this result, I would like you to work out what the variance-covariance matrix of my example from above has to be. Now remember that in that example, I set A to be 2, B to be 1, C to be 1, and D to be 4. You can then check to see that this agrees with the simulations, which it really must because we've taken so many draws from the normal distribution that by the law of large numbers, we should be very, very close to the population covariance and the population variances. So take a few minutes to work through this, pause the video, and then you can check your solutions against those from the course website. Maybe you've heard about the Cholesky decomposition. I think it comes up in macroeconomics somewhere. Well, today you're going to invent it. Unfortunately, that doesn't mean you can name it after yourself, but you can still enjoy that sense of satisfaction, along with the ability to remember it for the rest of your life. So, thus far, we have gone forwards. I told you A, B, C, D, and you were then able to find out what kind of correlation structure you would create between x1 and x2 when you pre-multiplied z by that matrix A. Well, now we would like to go backwards. So now we would like to find the values A, B, C, D such that we can achieve a particular covariance structure between x1 and x2. And again, we're still going to be taking this linear combination of z1 and z2. We're still going to be combining to create correlation. So let's start simple. For this exercise, rather not an exercise, for this slide, we're going to keep the variances of x1 and x2 fixed at 1, and we just want to create some correlation between them. So I'd like to create a correlation of 0.5. All right, so let's think about this for a moment. Well, if we look at x1 is equal to a times z1 plus b times z2. So if I set a equal to 1 and b equal to 0, well, then that would mean that x1 equals z1 and the variance of x1 equals 1. So maybe that's a reasonable place to start. Let's think about that. So what would follow from this? Well, what would then be the covariance between x1 and x2? Well, let's plug in this equality we just got. So we said if we set a to 1 and b to 0, then x1 is just exactly identical to z1. So that means the covariance between x1 and x2 is just the covariance between z1 and x2. All right, but what was x2? Well, x2 is this linear combination of the z's. It's c times z1 plus d times z2. So let's work our way through this. Using the properties of covariance, what are we going to get? We're going to get c times the covariance of z1 with itself. Well, what's the covariance of z1 with itself? That's just the variance of z1. But the variance of z1 is 1. So we're going to get a c. And then we're going to have the covariance of z1 with d times z2. But remember that z1 and z2 are uncorrelated, so their covariance has to be 0. It follows that if we set a to 1 and b to 0, then that will immediately imply that the covariance between x1 and x2 must be c. So that allows us to sort of pin down c. We need to set c to be whatever we want the covariance between x1 and x2 to be. But in fact, in this case, we want x1 and x2 to both have variance 1. So if the covariance between x1 and x2 is c when each of them has variance 1, then that means that their correlation has to be equal to c. So in other words, we just need to set c equal to 0.5. And if we do that, then we will in fact induce the appropriate correlation structure. Now we have yet to specify d. So what is d going to be? Well, remember, we need to make sure d is not going to affect the covariance between x1 and x2 on this particular slide. You can see that that only depends on c, but d is definitely going to affect the variance of x2, and we need to make sure that that's equal to 1. Otherwise, the argument we just made about the correlation is going to fall apart, and we won't have the desired structure. So what do we need to do here? Well, the variance of x2 is just equal to the variance of c times z1 plus d times z2. But because those two random variables are independent, the variance is just equal to c squared, the variance of z1, plus d squared times the variance of z2. But z1 and z2 are both standard normal, so that just shows that the variance of x2 is equal to c squared plus d squared. All right, but we already know what we need to set c equal to. We need to set it equal to 0.5. So if we solve for d, we see that we need to set d equal to the square root of 1 minus 0.5 squared. So in matrix form, here's what we've shown. We figured out what matrix we need to multiply z1 and z... Oh, there's a typo on the slide. Apologies. It says z1, z1, but of course it should be z1, z2. Apologies about that. I will definitely fix it on the course website. We found the matrix that we need to multiply z1 and z2 by in order to induce a correlation of 0.5 between them while still keeping their variances fixed at 1. If you found that moved a little bit too fast, now would be a great time to just pause the video and make sure that you can reproduce all the steps. There's nothing deep or sophisticated. I'm just using some simple properties of random variables. But I think it's very important to understand this simple example before we build up to the more interesting one that's going to follow in a moment. Let's check before doing anything else that this works as expected. We can set up the matrix A, which, as I mentioned before, should have the elements 1 and 0 in the first row, and 0.5 and whatever the square root of 1 minus 0.5 squared is in the second row. So here is my matrix A. Now I'm going to do exactly what I did before. I'm going to do my matrix multiplication, just bearing in mind the point I made about transposes and the bookkeeping that we usually prefer to have when we're generating correlated random normals, which is just to turn them on their side. And now if we, and by the way, the reason we like to turn them on their side is actually because the functions cov, like covariance, and core, expect them to appear in that form. So it's not just arbitrary. I'm doing that so I can easily interface with those functions. All right, so now we can compute the covariance matrix of this x, and indeed, it's exactly what we wanted. Well, close, because again, there's some random noise here. This is just a simulation. And just for fun, why don't we make our favorite 2D density plot? Now it's time for an even more exciting exercise. I would like you to modify the above argument so that I can obtain a correlation between x1 and x2 that is equal to rho, where rho may or may not equal 0.5. So maybe rho could be minus 0.2, maybe it could be 0.75. I want you to modify the previous logic so that you can give me any value of rho and immediately find out what the matrix A needs to be. But we're still going to keep the variance of x1 and x2 equal to 1. All right, then in the second exercise, we can try to think about how to extend this reasoning so that we can generate x1 to have a variance of sigma 1 squared and x2 to have a variance of sigma 2 squared, where the covariance between them equals sigma 1, 2. So you're going to have to extend your reasoning from the preceding exercise to find an appropriate matrix A such that A times Z has the desired variance-covariance matrix. Finally, I'd like you to check your calculations in the preceding part by transforming our simulated z from above into a matrix X so that X has variance 1, X1, I should say, has variance 1, X2 has variance 4, and the correlation between them is zero point 0.4. And why not make a beautiful density plot of your result? So as usual, please pause the video and then you can check your solutions against those on the course website. And again, the whole point of this, in this particular video, it's not to teach you the answer, it's to kind of guide you through this process of discovering the answer for yourself, because I really firmly believe that this is going to help you to understand the concept much better than me just showing you an answer or me just telling you a formula and asking you to memorize it. You just decomposed a 2 by 2 variance matrix sigma into A transpose. In other words, you found the matrix A such that you can get a desired variance covariance matrix sigma by taking A times A transpose. How do I know that's what you did? Well, it's because you already showed me that the variance covariance matrix of A times Z, where Z is a standard normal random vector, is A transpose. So in a sense, computing A is analogous to taking the square root of sigma squared. If I asked you, how do I take a standard normal random variable and give it a variance of 4? Well, you would think about this for a moment and say, aha, to get a variance of 4, I need to multiply by 2 because 2 squared is 4 and variance is quadratic. So multiplying a random variable by a constant scales the variance by that constant squared. Well, real valued square roots don't always exist. So there's no real valued square root of -4. And also, square roots aren't always unique. So both -2 and 2, when squared, equal 4. So the same issues actually arise for matrices in general, but so when I say the same issues arise, I mean not all matrices have a square root. And in fact, the square root may not be unique, but it is always possible, it turns out, to decompose a variance matrix into a decomposition of the form A transpose. So every variance covariance matrix is symmetric, but actually not every symmetric matrix is a variance covariance matrix. How can I illustrate this? Well, let's just pick a symmetric matrix here. It has 4 and 16 in the first row. It has 16 and 9 in the second row, so clearly it's symmetric. And now I'm going to use the function cov to core, which computes a covariance matrix to a variance matrix, or rather a variance covariance matrix. And what do we get? Well, that doesn't make any sense. It looks like the correlation between these two random variables would have to be 2.6. But correlations shouldn't come out to be larger than 1, so something has to be wrong here. And the something that's wrong is M is not actually a valid variance covariance matrix. There's something wrong with it. So just as variances have to be positive, any random variable at all, unless it doesn't have any variation in it, unless it's constant, has to have a positive variance. Variance matrices have to be positive definite. So we say that a symmetric matrix M is positive definite if V prime M times V, so this is the quadratic form V prime MV, is positive for any vector V that is not equal to 0. This is effectively the matrix equivalent of a positive number. So requiring that sigma is positive definite is actually, it's not just a technical nicety. It's actually extremely important. It's absolutely crucial to making sure that what we're doing here makes sense. So variances shouldn't be negative. If I take a linear combination of a bunch of random variables and I evaluate the variance of that linear combination, I shouldn't be able to get a negative number. Requiring that sigma is positive definite is ensuring that the variance of v prime x can't be negative. So in particular, for any v that's not equal to 0, this thing is going to be positive, and that is absolutely crucial. If you're a pedant, I can sympathize, and you may say, wait a minute, technically variances only have to be non-negative, and variance matrices only have to be non-negative definite. You're absolutely right, but the zero variance or the indefinite case is not actually important for this course and for most practical applications. So I'm just going to pass over that. We can always decompose a positive definite sigma into A transpose. So we can find an A that does the trick. But actually, that A is not in general going to be unique. So here are two matrices, A and B, and each of them satisfies the decomposition. So A transpose gives us the correlation matrix 1.5.51, but the same is true of B times B transpose. You can verify the algebra if you want. It's not terribly exciting, but there it is. I mean, sure, B does the job, but when you look at B, doesn't it look just a little bit inelegant? Doesn't it look a little overly complicated and cluttered? I kind of like A better. And what do I like about A in particular? Well, what I like about it is that it's lower triangular. If you're not familiar with the term, you can click on the link here to read more. But this is a lower triangular matrix, A, and it has positive elements on the diagonal. I like that. That's nice and simple. So the way that we're going to get uniqueness is we're going to impose an extra restriction that we want our matrix to be nice. And what's nice? Well, it's nice when the matrix is lower triangular and when it has positive elements on its diagonal. And that brings us to the Cholesky decomposition. Any positive definite matrix, sigma, can be expressed as sigma equals L transpose, where L is lower triangular. Notice that I've got that lovely mnemonic built right in. L stands for lower. L is lower triangular with a positive diagonal. This is the Cholesky decomposition, and there is the man himself. You can read some more about this decomposition by clicking on the link. But what's even more exciting is that you've just discovered it yourself. There's a command in R called chol, and what this does is it actually returns, it does return the Cholesky decomposition, but the thing about R is that it's a language that is built around a single letter. You guessed it, R. And so for some reason, the folks who designed R thought it would be more fun to return not the lower triangular matrix L, but its transpose, the upper triangular matrix R. So in R, the Cholesky decomposition is actually transposed. So this is a little bit irritating, but you get used to it. So when you do the Cholesky decomposition in R, it's actually going to be returning L transpose. That's no problem, of course, because you can just transpose the result if you like. Let's take a quick example here. I am going to check that this matrix A that I worked out before is in fact the Cholesky factor, so that indeed A transpose not only equals the sigma matrix that I've shown here, but that is actually the Cholesky factor. So let's do that. And as I said before, I have to transpose the matrix to get it to match up with R's Cholesky factor, but indeed it works. So what have we done here? Well, you thought up a way to construct the matrix A, and we sort of suggested that it would be nice to do so in this kind of triangular way, where we start off with a random variable z that doesn't get. I should say we start off with our first x that it only depends on one of the random variables z, and that gives us this nice triangular structure. Well, now we're ready to do this. We're ready to do this in some more generality, which you're going to be doing on the problem set. But in the meantime, I want us to think a little bit more about this idea of a positive definite matrix. So it turns out that there are some nice simple ways to check if a matrix is positive definite. First, you've got to check that the 1 element is positive. Then you can use the determinant function, det, to check that the determinant of the elements 1 to 2 and 1 to 2, so that's the That's the submatrix of the first two rows and first two columns. Check that that determinant is positive. Finally, you check that the whole matrix is positive. This will work for 3 by 3 matrices. For larger matrices, you've probably figured out the idea. You've got to look at all the submatrices that lie along the diagonal. So if you want to know some more about that, you can click on this link. I would like you to test whether each of these matrices is positive definite. I'm going to tell you that one of them is and the other is not. So which is it? Then I would like you to let sigma be the positive definite matrix from part 1 and play around with the Cholesky factor. Then I would like you to take a look at the R package MVT norm and consult the function RMV This is going to allow you to repeat exercise 2 the easy way without using this chol command, and also allow you to check your work. Finally, I'd like you to do a little calculation about variances. So in particular, if y is a linear combination of x1 and x2, and v represents the coefficients of that linear combination, then I would like you to show me that in fact the variance of y is related to the variance matrix of those x's by precisely this quadratic form.